of all, thanks a lot for inviting me. I am from a different domain, from computer graphics. So CG here in the title means computer graphics. So my question, my research question the last few years is really, can we use computer graphics as to support thinking in science, thinking in general, thinking like inventing new models in science? Let me explain what I mean. In fact, visual representation from the beginning of humankind have been mandatory to understand the world around us and to create also new artifacts, if you are an engineer. For instance, Leonardo da Vinci used this sketch here that you see on the left to understand the branching system in trees. He needed to sketch them. And to create this here you have a wheel. You will understand better when you see the sketch. Biologists, of course, it's the same. To express the story of cells that go through tissues to tissues and have to go between fibers and so on. It's so easy to understand with the sketch. So this representation in science, they help structuring ideas. They increase the intuition on the phenomena. But drawing indeed are limited because they are only two-dimensional. You would need drawing over time, and editing them is difficult. You just have an eraser, and it's impossible to interact with the drawing. And this is here that a digital image comes. What is good with digital images, of course, you can reconstruct capture data. But when you reconstruct capture data, in fact, they show only one specific instance of a phenomena, and you cannot easily choose which instance. There is no possible interaction. And also, it doesn't help for abstraction. So it doesn't play the same role as a sketch. Then scientists can move to 3D modeling software. Here, I am taking an example with Didier Roux, who is a physical chemist, who is also a member of the Academy of Science. He came to see me a few years ago because he wanted to model the changes between isolated bubbles to strip phase in the mixtures of liquids, for instance. So he wanted to explain and to see visually his hypothesis, his mental hypothesis about the transition to sponge phase. So he can express to a computer artist what he wants, and the computer artist can tune, for instance, Blender, Maya, this modeling software in order to have this. But it will take time. And the problem if you do that is the vision from the scientist need to be explained to somebody else, and it will not correspond immediately. So you have lots of trials and error. It's a tedious work. And when it is finished, when finally you see this animation, it's a sterile 3D illustration. The scientist cannot interact or refine his model, because the scientist, when he sees that, he may want to zoom, to add detail, to sketch detail, and to refine his thinking. This is not possible with current modeling softwares. So in this talk, a previous version was called user-centered creativity. It really says that. Could we use smart 3D environments as visual testbed in science, or if you like, to help scientists expressing their mental vision of their phenomena of study. And for this, I will introduce first a methodology that we had already for modeling 3D shapes and 3D environment in computer graphics, and then explain the first applications that I did with scientists of other disciplines. So we will go through a wide set of applications. Sorry, I will not be a lot detailed, but I'm not like you, really mathematician. Okay, so for the methodology, the first part is that we need to have real-time simulation, even if it's only a visual simulation, because if you want to have a virtual test bed and be able to sketch and to animate things immediately, you need that the response of the system is real-time. So I will explain how we can achieve this using layered model and embedding knowledge. And this expression of knowledge is another part of AI, in fact. It's like an expert system, if you like. Then second part is expressive design. How can we use sculpting gesture, sketching gesture, copy-paste, which we call transfer in computer graphics, to be able to quickly model what we think about. And then learning from examples. Everything cannot be expressed by law. Maybe we don't know the law yet. Maybe we have some examples. What can we do with them? If you want to express this mental vision. I will then go through some applications from geology to ecosystems and to paleontology. So the first challenge is to have real-time simulation, and to explain this layered model, I took a very old example that I did with a long time ago with my PhD student Florence Bertaille, which was a hair animation, but it's a good example of this layered model. For instance, if you want to animate a full head of of hair. Here it was a collaboration with L'Oréal Research, so we were seeking some realism. They wanted to try cosmetic product on virtual head of hair. And we are working with Basile Odoli, I'm sure you know him, who did the mechanical model for a single hair strand. And of course, hair strands, they don't change length. So if you simulate them with a finite element, it's very stiff. They don't change length at all. There are only degrees of freedom at 2 curvature and the torsion. And so the difficulty with hair is that in a full head of hair, you have 200,000 hair strands. And all these hair strands interact together. So they have friction, they have collision. And if you have numerical simulation of their motion, the problem is that from a time step to the next, they can pass through each other. So detecting collision and processing collisions is extremely difficult. But if you suppress the collisions between the hair strands, then the hair will just be near, colliding with the head. So all at the same place. So you will not have the hair volume. So this is why it was a difficult problem. And to this, we applied a methodology that we invented earlier in computer graphics, which is when you have this kind of problem, you try to decompose the problem in sub-phenomena. For instance, the first one is a dynamic of hair. The second sub-phenomena is the fact that there are collisions within the hair strand. And the third one is that there are lots of hair strands that should be visualized. For each sub-phenomena, you find the best possible representation. And at each time step, you will animate the first sub-phenomena, then the second, using the result from the first, then the third, and there can be some retroaction. And so this ensured, coupling these submodels ensures the coherence around time. So for instance, for the case of hair, we use superhelices, this constant length strand model for a few guide hair that were selected with, and this was sufficient to modeling the dynamic of the hair. And then we use a volumetric wisp model and tracking closest point between neighboring wisps in order to have the collisions within the volume of hair. And then we use some geometric strands, either interpolating in kind of straight regions or extrapolating the guide hair, in order to display the full hair. And so this is the results we obtained at the time. So it was 2006, where you could, in computer graphics, very often you have to show side by side the real phenomena and what you can model. And we did that just to show, we took the same hairstyle and simulated the same kind of motion, just to show that visually, this is what I call visual simulation. We don't prove that it's correct, but visually it can express what we want to express. And so this can be done for straight hair, but if you set some rest curvature to this hair, you can have hair strands that are curled, and when the motion is quick, like for this dancing motion, then the wisp of hair will extend, but at constant length for each strand, like a kind of spring that extends and comes back. Of course, what is nice with this methodology is that each submodel can be adapted to the needs. We had other work that I have no time to show here, for instance, where we use an adaptive tree of hair, because sometimes you need less individual wisp at the top of the rest of the strand and more at the bottom, especially for long hair. And this can be dynamic and change over time. So the second challenge, if you want the scientists to be able to create, we want to animate in real time, but we want also to have expressive design based on intuitive gestures. And in real life, a good example of expressive gestures is clay sculpting. We are used to be able to interact with materials. So in my lab, a long time ago, we did this real-time model for virtual clay, exactly the same mechanism. It was based on a layered model. So, but to sculpt clay, you need to have a hand model, and we designed a hand navigator, a device, where with your hand, you apply pressure with your fingers, and each time there is you capture the pressure for the real finger, it will curve the virtual fingers. So it enables to sculpt. But people can also sketch much more easily than they sculpt, most people. So we are also interested in sketch-based modeling system. This means enabling people to do figures in 2 dimensions and deducing the 3rd dimension from what is sketched in 2 dimensions. So this is an example of this using implicit surfaces. So how can we now extend this to embed knowledge in this sculpting and make it usable for in case where we have knowledge? So then for sciences, where this model will have knowledge. Let us start with a simple case. It's a man-made shape. You have this castle. And this castle is a good example of structured shape, where in fact the shape has some self-similarities and some local symmetries. This is true as well for natural shapes. This kind of shape can be expressed by so-called a person shape grammar. This means that the shape can be decomposed in subparts, for which you can define a transformation grammar, like the grammars for languages. So, for instance, if you take this castle, but you remove B, it remains a castle. If you exchange A and D, one is a tower without flags and the other is a tower with flags. It remains a castle, and you can insert B. So you have a set of rules. And of course, we could apply all these rules. This rule has random, and we will have a huge castle if we apply them at random. But what I said, I'm working on user-centered creative AI. So I want to put the user in the loop. So what we did instead is a sculpting system where these rules are applied, combined with a physically based model. Here, the user is pushing on the castle, as if the castle was clay. He can cut, and each time the rules, the necessary rules are applied on the fly so that it always remains a castle. So in this case, for instance, the user can in fact sculpt a very small medieval city in a few gestures. So you see the methodology. You put this knowledge like an expert system in your model, and then it's applied depending on the user's gestures. So now let me speak of the first example of collaboration with scientists of other disciplines that we developed. So this was with a geomorphologist called Jean Braun, who was in Grenoble at the time, but how he's in Berlin. I'm sure some of you know him. And so the question that we ask ourselves is, could we sculpt mountain ranges as if they were clay, exactly like we did for the castle? What makes it easier with mountain ranges is that they are due to the collisions between tectonic plates. So we will not need to have a virtual hand sculpting, like for sculpting the clay in 3D, but we used a touch table, for which we put our hand on it, and we push tectonic plates, and we want them to be able to form, in fact, these mountain ranges in real time, to be able to understand really, seeing things in real time. It's very nice to tune the models to better understand and also to explain them. For instance, in a science museum, this is something that would be really useful. So Jean Braun explained us the main phenomenon, which is that when you have these two colliding tectonic plates, so it's a volumetric material, you have layered sheets of material of different width. And so the uplift of the mountain is caused by this collision. And you have these folds that appear, and then at the same time that it rises, it's uplifted, the mountain erodes. So we have erosion as well to be simulated. So to solve the problem, we use exactly the same philosophy of layered model than for hair animation. The three sub-phenomena that we identified is that, roughly speaking, this Earth crust is to deform at constant volume, and this is why it raises. So first thing is constant volume, and this is the first sub-layer that we use. Second thing, we have the folds that depends on the wavelength, okay? And third thing, we have the erosion that should be applied on top of the uplift. And we apply this to a volumetric model of this Earth crust. What is really interesting when we say that is that the first, is a simple model of constant volume. The second one, in fact, we don't need to have a complicated finite element simulation of this. This was done. The geomorphologists did finite element formulation, but we also look at the literature, and it was well understood that, in fact, the frequency, the wavelength of the fold, depends on the thickness of each layer, on the material and on the thickness of each layer. So since we knew from the thickness of the layer which frequency of fold we wanted, then applying them, without simulation, as a procedural knowledge-based model was perfectly fine. We don't need to resimulate something where we know already the result, of course. And here we wanted something real time. So this is the result. Here you see the fingers of the user on the tablet. And we are using the fluvial erosion model that we developed also with Jean Braun. So each time we push on the mountain at the same time is uplifted, but also erodes. So you see all what is formed by the river. And we can see the cross-section because we simulate a volumetric model. So we can cut our mountain and also display the cross-section of the model. And what is nice for the geomorphologists is that for the first time, they could see in real time and in 3 dimensions the results of their model that they had already, of course. We didn't invent with them a new model, but they were not able before to see this in real time. And in terms of computer graphics, what is really new is that when we erode these volumetric terrains, we see the different layers of earth on the eroded cliffs of these mountains. So this is really interesting because when we capture, even with modern ways of capture, we capture real terrains, we have only the surface. Here we have everything in the volume, so it's very interesting. And if you want to touch this, to do that, come to the Museum of École Polytechnique, because this installation is for display at the Museum Musics of École Polytechnique. So you can try it. You can sculpt. It's a kind of cube. You sculpt your mountain. It's a cube with several screens. You sculpt your mountain on top, and on the side you see the cross section of the mountain. Okay, so this was for sculpting. As I told you, sketching is sometimes easier. For instance, I would not be able to sculpt a tree, for instance. So we also worked with biologists of CIRAD long time ago on how could we model a tree, a realistic tree based on biological law from a sketch. This is kind of very interesting because, of course, the user cannot sketch every little branch and every leaf of a tree, and it would not be realistic. It would not follow biology if you did that. But in fact, biologists from CIRAD, exactly like artists, when they go to the forest and they want to observe the evolution of their tree, they use multi-resolution sketching. They will first sketch the rough silhouette of each group of sub-branches, then they refine into sub-branches, and then they refine again. So we found the same strategy from artists and from scientists to go from coarse to fine, to express what they see, their knowledge. So we had this idea of providing a system, a 3D modeling system for trees, that from the structure, from the silhouette of the tree, the coarse silhouette, would little by little enable us to compute the internal structure and to add knowledge from perception and knowledge from biology, from phyllotaxy. So it works as follows. In fact, the user will start drawing a silhouette. From this silhouette, we'll compute a kind of skeleton, the medial axis, but we keep only the endpoints, and then we compute the best branches that will lead to this medial axis, and we can change phyllotaxy, change the orientation of branches just by a sketching gesture, and everything is recomputed. Then the user can zoom on a subsystem, sketch again to give the density of sub-branches they want, etc., until they go to the leaf level. And then when they zoom out, they have their 3D tree reconstructed that follows the laws that we have put of biology and some laws of perception as well. Because it was demonstrated that when you sketch, seen from above, if this is your camera, you will sketch only branches that go to the side. Never we sketch branches that come to us or that go to the back. So these ones need to be duplicated, inferred from what we sketch at the side. So this is a bit old work, but I think this is a very good example of what we want to do. So here you have, it's an expert system. It expresses knowledge from biology. At the same time, the user can interact. And the user is helped by this kind of smart graphic models that will also build automatically this construction line that you see that helps zooming. And we know that the tree is self-similar, so we learn then the statistics of the sub-branches and copy-paste the same statistics at the same level everywhere. So once we also put them in 3D. So once we zoom out, we have a tree that corresponds to the species we have chosen and correspond to the sketch. So this was the first work where we had to use learning from example, because in fact this was when we were sketching these little bumps on the branch, it was a statistic distribution finally of the sub branches, and we started here to learn the statistics. Later in our research, we wanted really to do that because what we wanted to enable is a modeling of a full natural scene. You see, for a very long time, I was in position in Grenoble. So this is near Grenoble, very nice place in Chartreuse. And so how can we learn consistent distributions of all these elements? And what I will show you is that we have two strategies for learning. We can use from user-defined example or from real data, but we can also learn from simulation results. And both are interesting. So what our first work now to populate this virtual world with elements was called the world brush. The idea is to give a painting system to users, but where users will be able to paint distributions of elements. But I would like a smart brush. I would like that with my smart brush, when I pass on a place which is really steep mountain, I would like to have only rocks. And when my brush goes to places which are flat, I would like to have a distribution of trees and some grass in between trees. So the idea is that the user will design by hand a single example. This is nice because it is what I call light learning. Light learning from a real time from a single example. So it doesn't use too much of the world's computational resources. And so, of course, it's borrowed for you, applied mathematicians to statisticians more precisely. So it's point processors. So the idea of point processors is that from each point of a category, we look in disk around it and have histograms describing the number of the distribution around them, the number of other elements they have at various distances. It can be done for the same ratio of elements, from tree versus tree, or tree versus stones, and we did it also, we extended to slope, and other element, proximity to a river, the slope, we had other kind of histogram. But from a given exemplar, you have a series of histograms. And then this histogram as if it was a color in a palette. So this is a specific example, user-created example, a series of histograms. This is another series of histograms. And then with your brush, you will choose your distribution in your palette and paint in 3D your virtual world. So this is exactly what we did, and here you see, and we see this how it is used. Here you can just have a pipette tool from the user example and copy it. But when I use the brush is smart enough to put the right distribution at the right places. You can also take your little forest and move it around, and you see that it adapts so that the statistics are always good from what was learned. And you can have a gradient between these colors. But for the gradient, you should use optimal mass transport in the domain of each statistic, of each histogram representing it. And it was very interesting discovery that optimal mass transport is what expresses what we want. So here you saw the user painting with a gradient brush. And here we see the scene carving. This is when you want to have a deformation. How do we make it stable for the user? Okay, so we did it also for, we extended it also to have alignments and to learn the angular distribution and so on. And at the end, in a few gestures, the user can create a virtual world which is kind of self-similar, but nowhere exactly the same. This is what is important, like our words. We could even do it for distribution of houses along trees and so on. So this looks like a toy, and you could say, okay, yeah, but why is it related to what interests us? But after that, we worked on, we extended the system to be able to learn from simulation results and maybe closer to your interest. So imagine that you have a terrain, and on this terrain, you have lots of maps that will express the different things that you have, the altitude of your terrain, how the mountains are oriented towards the sun or towards dominant wind. Maybe it could be also the nature of the geology of your terrain. So each time it's the same color. We did a means clustering. Each time it's the same color. This means that you have exactly the same conditions. And then for each of these conditions, you can model plant growth using a sandbox simulation. So it's like the simulation we do in graphics, or you do, it's a particle system, if you like, if of them represents a tree. Maybe I have some details just after. No, I didn't put in this presentation. So let me explain better. Each of the tree, in fact, is a competing species. It's not these particles, it's like two disks. A disk for the root system and a disk for the canopy. The canopies are competing for light, and the root systems are competing for Earth resources. So when you simulate in this very little round pieces, you seed some plants, and you model, you use a grid, for instance, you do a Eulerian simulation, and you simulate the competition between these species, and each tree would have a health factor, and each healthy tree would be able to seed the trees of the same species around it once a year, while those who are not healthy, they have a probability of death. And then after a few years, you can have the evolution of your ecosystem. Now the idea is to use exactly the same as wall brush, but now we will use a pipette tool from the simulation results. So we will be able to say, okay, I suppose that the forest has burned, and I take a forest which is only 10 years old in this area. So I learn the statistics, and then I can brush my terrain with these statistics. So in fact, we call this semantic brushes. The user now can have, for instance, the African savanna, or a Mediterranean landscape, or this is the Grand Canyon with the Mediterranean ecosystem. This is an alpine ecosystem. So we can have this now with these semantic brushes. It's fully consistent ecosystems because they are learned from simulation results. We still have some user control. For instance, in the African savanna here, we model the destruction by big animals and by humans. So this is why it's not fully uniformly covered by this small sparse vegetation. To solve this, point processes pre-existing in statistics were not sufficient. Because when you have, for instance, a Mediterranean ecosystem, you have some plants that only grow underneath other plants because they don't need so much sun. Take the mushrooms, for instance. And you have others that really need to have their full sun. So in fact, we needed not only to learn distributions of points, but to learn distributions of disks, which may have specific loads. So in fact, what we did is that we use PCF, which is pair correlation function, which is like a smooth version of the histogram. This smooth and normalized version of the histogram is really great because it enables us to do gradient descent when we want to converge, when we put points and we want to converge to a given distribution that we store in this way, we can take a gradient because it's a continuous way to see our histograms. And with this different, in fact, distance function, what we could express is, do these species overlap or don't overlap? They're nested one inside each other, and it's enabled to reconstruct much better this kind of ecosystem. After that, I'm working in computer graphics. In computer graphics, we love animations. We thought that it was a bit sad to have all these virtual worlds without any animal on them, without any animation. So we wanted to in fact extend to populations of animals. And here, having the rules, as I told you, in some cases, we could not even simulate. We are not sure of the rules that make that sheep always remain in herds. I mean, there are some hypotheses. There is a void model. We have to tune parameters. We are not sure it corresponds to real life. So what we decided is to work on a pipette tool from real photos. We set it here as an authoring tool for computer artists that want to create a virtual world. So this is why in my example, there are photos from different species, but of course you could do it with the same species. So imagine that you want to animate a bird in your virtual world that has a given trajectory, and you want to say, okay, I would like that at this point of the trajectory, it looks a little bit like the distribution in this photo. And then at this other point, I want that it looks like this distribution, which is really different. But the problem is that in the photo, you don't have the same numbers of animals. So it's really difficult to do that. So, but thanks to our statistical learning mechanism, we extended it to ellipsoids instead of little points or disks. It's ellipsoid that should not, of course, overlap in this case, okay? And then we learn the distribution. And so this means that from the photo, we can resynthesize the same distribution with the control number of elements, say 200, for instance. And then we can resynthesize what we learn on each photo with the same number of elements. And then we design some interpolation methodology. Is it here? Yeah. So you will see it more in detail. So, we do just little prototypes to show that it's usable. So here the user is just tuning the trajectory, tuning the photos from which they want to learn, and orienting them as they want. And then they deciding to have, I think in this example, it's 50 50 animals, you will see the 50 animals start with the distribution in one of the photo, 200 here, sorry. And so we had to make the correspondence and to synthesize the motion in between, of course. So here they are from the statistics that were learned here. Then we let us go a little faster, and then they will reach another part of the terrain when they should adjust to another photo, for instance. So this is a kind of author. So just to show you that in those authoring tools, the scientists who want to express something could think, create by the example by himself. He could use simulation if he knows the rules and learn from the simulation, but he could also learn from static images. And we are working right now on how could we learn this from videos, but we didn't achieve yet. The last part of this talk, the last 10 minutes, I will tell you how we worked recently with paleontologists. In fact, in 2017, I was very lucky at a conference in France to make the famous French paleontologist Henri de Lumley, who discovered the Grotte de Totavel, Arago, which is, and he discovered the first Homo erectus who lived in France 500,000 years ago, and which is the ancestor of the Neanderthalian. And we had even a full team meeting several days with in Totavel. And what paleontologists, prehistorians told us is, with computer graphics, could you help us to see our models and even to be immersed into our models? Because in their case, they use sketches. They explain what they imagine to artists, and they have the artists manually sketching for them the results of their investigation. Because in this cave of Totavel, they have pollen, so they have knowledge about the ecosystem. They have little animal bones, so they think of which animals could be there. They know about the climate. They have lots of knowledge. But if they need to explain to artists, this is what it gives. And else they have in their museum in Totavel, they also have mannequin. And so they try really to see in 3D what they have. Could we help them to see it better? Could we go further with them? And so we started, in fact, to extend our research to design for them a consistent authoring systems for landscapes with not only flora, but flora and fauna. Because for the moment, the plants and the animals were never correlated, neither in prehistory, but not in computer graphics as a while. So what we decided to do, so we had all this input. So the terrain, this is the Totavel Valley, which is in France, you can go there. There is a paleoclimate that we knew about. So we had the illumination of the terrain, the hypothesis of the temperature, but we had it at various points in time. We have at these points in time the moisture. We have lots of maps. From that, what we want to see is ecosystems that are consistent and enable the paleontologists to be brought in 3D, immersed with virtual reality into their scene, into their model. And then we want that the model has not only plants, but also animals. Of course, the animals, when you go to nature, you don't see them every day, but what you can see is their eroded trails. So we wanted from the main routes of animals to be able to compute the eroded trails. And so this was really interesting and really challenging. And we designed a multi-resolution system for solving this. So the idea is that from all the maps, we can see the plants, which are the resources for the herbivore. So it's a little bit like the ecosystem simulation I was talking. It's another version of the ecosystem simulation I was talking about. So it's not seeding the plants were not too difficult. What is really new is to be able that from this we express the different sources of the nutrient for these plants as resources for the herbivore. And then the herbivores themselves became resources for the carnivore. So we have a kind of multi-resolution graph, which and in fact, each connected part of the graph represents the territory of a given herd of animals, or maybe an individual animal if it's an animal that hunts alone. But you see, for instance, this group of animals cannot cross the river, for instance. So it's a different connected component here. And here you have other predators that can go from here to here. And so at each level of the food chain, you have this graph which is computed. And different from you all know the prey-predator simulations that are done with differential equation. We wanted to differ from that because the prehistorians, they have found specific proportions of each plant at a given level. When they dig into the Cône de l'Arago, they find a proportion of pollens of different plants. So they have the hypothesis on which plants were there, which proportion, which animals. And we don't want to simulate the dynamic of a system that will diverge. Because if you played a little bit with prey-predator system, you may know that you start with a given distribution, but it's very likely that after a few steps, some species will disappear, and because the other species will have eaten them all. And this is not what we wanted. We wanted really to show to the prehistorians a kind of equilibrium ecosystem that express what they have found in the cave. So to do that, in fact, we made a quasi-equilibrium state hypothesis, saying that species are only allowed to eat each year the surplus produced by their resources. And then we use a greedy algorithm to be able to find the number of herds of each animal that we use. This means that, imagine, for instance, we seed the plants, the trees, and so on. Some plants have the resources for the herbivore, but they produce this amount per year. So we take all the herbivores, the one that needs the most resources first, and we seed them herd where there is this plant. And then if the territory, they cannot cross the river, so in the other side of the river, we seed another animal, and so on, and we go up like this, taking care of their resources. And so finally, the result of all that, I will not detail too much, is that, yes, we validated. In fact, we took a Bryce Angel Valley, which is a part of the Grand Canyon, because we were asked by seagraph reviewers for validation. And we were able, in fact, to compute our ecosystem in this landscape. And we were able to compute the trail that we have for large animals with the routes that we see in satellite data, even if the routes are the routes for 4x4. I mean, they are the routes for cars now. But this was a nice validation. After that, we provided two things to the prehistorians: the full 3D landscape that they can explore, and they can go and see their animals, and they can also have a map view when they see the different herds. And in fact, I didn't say, but we have a daily pass of the herd, because the herd needs to feed. So we designed, or we computed automatically some daily path for them. And here, so you see one herd of grazing deers. And if we go a little further, you may see a lonely deer, which is walking here, and elsewhere some wolves. And based on their daily path, as I said, they erode some trails. So you see also the trails that the animals leave behind them. Okay, and what is nice as well is that we had this for different climate, and I will not detail because it's almost the time. Okay, so too bad, because I wanted to explain you what we did more recently. Can I still give a few words on that? Okay, more recently, what the prehistorians really want us to do is to simulate pre-human activities. And this is even more difficult because we are dealing with the Homo heidelbergensis. As I said, is the ancestor of the Neanderthalian. So we don't even have a full skeleton. They have a piece of skull, and they have a few bones. And all the bones they have found come from different individuals. So they don't have at all a full skeleton. So they have some hypotheses, but they are very coarse about their morphology. But what they have found in the cave is that they were able to hunt very large animals. In their cave where they were staying in some seasons, because they were moving around, they found, for instance, mammoths, but they found also very large reindeers that were really massive. And they find 170 of them in the same layer at the same period. So the prehistorians would like to say, to know if it was in one season or in 10 years or in 100 years that they brought all this. Because for us now, it looks like the same layer in the cave. Okay? And so for this, to be able to answer the questions of the paleontologists, we have to reproduce locomotion in this natural environment. So this is the Totavel Valley now, but it was a bit different earlier. We have steep slopes, sliding rocks, snow, mud, depending on the time, swamps, rivers to cross, dense vegetation, and we have to simulate these unknown humans on that. So how can we do something useful? This is really interesting. What we decided is to design for them a simulator system for pre-human mobility. And our project is funded by CNRS. It's called PaleoMob 3D. So what we do is that we have two levels. At the course level, we will do some motion planning. For instance, we know in the cave that they found, for instance, some flint tools. So prehistorians have found where was the source of the stone. So now they want to know how long it took them and where they were going through to go there. So what we want to do is a motion planning to find the path and to find the time it took to take their resources. And then second thing, we want to be able to zoom and to reconstruct pre-human locomotion, which we can do, for instance, using deep reinforcement learning, but this is just starting. I just started with an intern last spring. So this is, I will not show you results about this, but there is a lot to do because nobody trained a physical model of deep reinforcement learning that need to infer the muscles to stay in equilibrium and walk over time on a slope and on a muddy terrain and a terrain that moves when you walk on it and through vegetation. But for our first work, what we did was this motion planning. To do this motion planning, in fact, we added an hypothesis, which is to say we suppose that the power spent during these long walks was constant. I mean, at each instance, I'm using the same energy to walk. So if I'm walking on a slope, I will go slower. If I'm walking on the mud, I would go slower, for instance. And then if you say this means that then we can compute the power used in walking as this constant power minus what is dissipated by interaction with the environment. And so if you have a walking model, then you can deduce the velocity from the power you have. And what we did is that we borrowed a walking model, in fact, from colleagues from Academy of Science, who are in fact Jean-Paul Lomont and Alain Berthoz. Together, they had proposed an analogy for human walking called the yo-yo man. In English, we say rather the rimless wheel. And this is to say that if you are a human that walks with a leg of length L, with a mass, a given mass, is exactly the same as a wheel that will just roll on the ground. And it's like if the virtual wheel was rolling, and I just use the same energy because, in fact, the only energy expense is to raise my center of mass and then make it fall on the next step. So exactly like this wheel. And this enables us to formulate what is the velocity depending on this power used for walking with this simple model. Then we also formulated using a soft ground model and using energy spent by slope, what is dissipated when you interact with vegetation. And just to show you this last result, so here this enables us not only to reconstruct, so we had now the speed at which you could go from a point to another. So this means that we express our terrain as a directed graph. And we weighted each edge of the graph by the traveling time given our model. So, and then we computed the shortest path in this graph, which gave this white line. And now you can see the wheel and you can see the virtual human that goes at the speed that we computed. So it goes slower when it is coming on a slope. So it is using always the same power. And we think that this path is the most probable path. Not to have too much energy when you go from a place to another. And this enables us to compute these maps for the paleontologists, so which are the most probable paths where they could go to reach the points where they gathered their resources. Okay, so in conclusion, what I have tried to show is that you can try to use creative graphics as a way to help scientists to express their mental vision of their object of study. And I think it can be very good for scientific thinking because being immersed in their model, seeing something and being into their model in a sense, being able to interact with their model in real time and also to zoom and refine them is excellent. Currently, I didn't have time to speak about that, but we are also collaborating with biologists, with Jean-Luc Cole, who is in Grenoble, on this kind of application, which is going to the world of something which is much smaller. It's a cut from a skin tissue, and you have all the cells that should be animated, and it's something that is also interesting. It's like a figure that will be 3D animated, created interactively, and that you can zoom on it. And what I see here also is that in contrast with what people call creative AI, what I want to do in my research is to use smart model to make us human more creative. Thank you for your attention.
Okay. Merci beaucoup pour l'exposé très intéressant et surprenant. S'il y a des questions.
I have a question about your method of work. This is very impressive development in graphics, which would take tremendous number of hours for somebody who doesn't have your experience. So how do you do? You have blocks of things already. You have libraries, of course, from the web.
Yeah. But the main point is that I need a lot of PhD students because I'm not coding myself, and now graphic coding on the GPU with all that, so they are very efficient. And in fact, we need to have a student per project in a sense, okay? And but once we have, what is very nice is once we have the system, then we can create lots of things with the same system. Of course, we only do prototype because you know what it is. When we have a PhD student, he will be gone after 3 years. We don't have the money to maintain an engineer that will gather all what the student implemented. And very often, like maybe some of you, we kind of lose the blocks that we had already implemented. This is a pity. But thanks to systems such as Unity, for instance, also the industry integrates little by little the blocks that I have. For instance, I said that now we are working in deep reinforcement learning to recover the gait of this prey human. But in Unity, they have implemented a library of physically based 3D simulation, which I can use. I don't need to have my students re-implement it. And also, they implemented in Unity the PPU algorithm for deep reinforcement learning. So this means that now they can find 2 libraries that they can reuse, and we focus for each PhD on only the novel point.
This is a game company, right? Unity.
Unity is a game company, but they provide for research. Their software is free for research.
Is the game industry integrating on your?
Unity is not really a game company, but it's a provider of a development platform for games. So exactly the same. But there is Ubisoft, which is a game company, and we collaborate with Ubisoft. For instance, when they saw the way we are painting with brushes all these little elements in virtual worlds, they still had in Paris hundreds of artists putting by hand each little brush in their huge virtual worlds, and they were working in parallel, and every night they were putting together all what the artist had done. But if one had moved the tray, the other one had the bushes that are in between the tray, so they needed to undo what they did the day before. It was complicated, and now they implemented this learning from statistics. So what we publish goes sometimes quite quickly to the industry.
You find them in your computer game. Any other questions?
Yes.
Did you work with neuroscientists? I know that there are models creation of faults in the brain corresponding to strength and elastic energy, minimization of elastic energy. That looks maybe a bit what you showed with erosion.
Yeah. I didn't work directly with them, but my colleague Puran Memari is really interested in this application and did something. And I know that it's a potential application. I even have the contact, but I don't have time to do everything. And yes, it would be interesting also to model the human brain. What we did is a multi-resolution model for the visualization of white cells, of fibers, of neurons. Like a multi-resolution model when you can zoom and see like tubes, like large tubes, the groups of neurons that go from a zone to another, and then you can zoom and subdivide and so on. So, but not the faults. We didn't model the faults.
You said you wanted to be interactive with the scientists. How does it? How can it be interactive? You have some kind of rules that can be changed.
So it's completely. I showed a variety of things. So it's completely depends. For the example where you give the little distribution and then you want to have a graph that will find them, this is fully interactive. For the case of the ecosystem, it's maybe take a few minutes. Scientists need to give the list of species they want from plants and for animals, and then regenerating the full 3D animated virtual worlds may take a couple of minutes. But then when you are immersed with virtual reality into this world, then you see everything in real time. So yeah, it depends what you call interactive, in fact, it depends on the application.
Was not this scientist eager to do it?
They are
Or
historians, they're extraordinary. What they want to do, imagine they want to go and hunt with this prehistoric man. So they want us to use artificial intelligence to recover how they were trapping with their light tools, how they were trapping these large animals, and they would like to go and observe them, okay, and hunt with them. So they have dreams, and I think that these dreams that they have inspire us. So what we do is not at the level of their dreams, of course, but it's very nice too.
That brings another question. Do you see future in these 3D things where you have a mask and gloves and things, and you could do the same thing with that?
Yes, we could. So we could go there using virtual reality, but we have really problem is that we have only the vision and the hearing has senses. For instance, if we go to I don't know, glacier climate, I will not feel feeling the wind, you will not feel the same thing. But what we are working on is how we can wear this virtual reality set and use gestures to train the deep reinforcement learning agent. Because these agents, they are trained by imitation. They train much easily. Their training will take less time if we give them some example motion. These agents, they have a different morphology from us. But if we show them the motion and they try to imitate the motion, then later they will optimize the energy they use to do it. So the motion will become adapted to their own morphology. So this is how we will use also virtual reality.
Est-ce qu'il y a des questions en ligne? I have another question. When you want to be predictive, for example, for the path which will be less energetic, how can you check if this is correct or not?
In fact, we checked with the hiking trail. In fact, we took, this is a hiking spot, and people often hike from the cave to this hiking spot. Okay. And what we did is that we computed, then we corrected a little bit the map by putting the map of how it is now.
Yes.
And then we may had our model compute to see if the trace that we had was consistent with the trace that people take now, and if the time was more or less consistent as well. So this is a trail from now. This is a hiking trail. This is really what the prehistorians were interested in. Of course, we cannot validate really all that, but it's better than nothing, I would say, for them. Yeah. Okay. And it makes kind of sense. Look, for instance, here there is a river and there is a gorge, which is very steep. And our models find out that to go there, they have to go up the gorge and to cross it at a place where they can cross. I mean, what the model computes makes sense. So.
Could you know what you do when you are breaking this bigger problem into blocks and combining them mathematically, combine sort of splitting scheme or something like that? What do you do to check the errors that you do by breaking and reassembling the problem into blocks?
I would say that
you will observe, I don't know, that occasionally you have a tree on a rock and you should not be able to grow that fast.
So in fact, I'm not thinking in terms of error because I'm not looking at a predictive simulation with numbers that I compute, and I don't have ground truth in many cases to compare with. I'm just looking as an expressive sketching system. Imagine that these people can always, these scientists can sketch what they imagine with the paper and the pen, and I just try to give them a more intuitive and faster and more expressive sketching tool. And if they are not happy with what they see, then that means that they need to input more laws in our model to tune the parameters, but it's them who should tune the parameters, not me. Okay? They have sliders, they can tune their parameters. For instance, if they're not happy with that, they can have other hypotheses on the mass of this character. Maybe the length of the leg was not the right one. I don't know. This is In a sense, this is their problem because what we design is a prototyping system for them, which is real time. So it's a bit different from applied mathematicians who try to simulate something based on obtaining things that look like real life.
Okay, so in some sense, if you have your elements like a huge rock on top of a tiny one, it's something that you correct by adding.
Yes, exactly. We have the rule of gravity, we have the rule of erosion. This large rock will certainly finish by rolling out of the small one. Certainly. It depends on the rule we implement.
Ok, ben, s'il n'y a pas d'autres questions, on va te remercier encore.